In the war of currents era in the late 1880s, George Westinghouse and Thomas Edison became adversaries due to Edison's promotion of direct current for electric power distribution against alternating current advocated by several European companies and Westinghouse Electric based in Pittsburgh, Pennsylvania, which had acquired many of the patents by Nikola Tesla. The direct current system generated and distributed electric power at the same voltage as used by the customer's lamps and motors. This had the effect of large, costly, distribution wires and forced generating plants to be near the loads. With the development of a practical transformer, power could be sent long distances over relatively small wires at a convenient high voltage, then step down to the voltage used by a customer. Alternating current generating stations could be larger, cheaper to operate, and the distribution wires were relatively less costly. As the competing systems were protected by patents, there was commercial rivalry between the Westinghouse and Edison companies. A publicity campaign by Edison highlighted the safety issues of high-voltage transmission. The lower cost of AC power distribution prevailed, though DC systems persisted in some urban areas throughout the 20th century. Background. During the initial years of electricity distribution, Edison's direct current was the standard for the United States, and Edison did not want to lose all his patent royalties. Direct current worked well with incandescent lamps, which were the principal load of the day, and with motors. Direct current systems could be directly used with storage batteries, providing valuable load leveling and backup power during interruptions of generator operation. Direct current generators could be easily paralleled, allowing economical operation by using smaller machines during periods of light load and improving reliability. At the introduction of Edison's system, no practical AC motor was available. Edison had invented a meter to allow customers to be billed for energy proportional to consumption, but this meter worked only with direct current. As of 1882, these were all significant technical advantages of direct current. Alternating current had first developed in Europe due to the work of Guillaume Duquesne, Gans Works, Sebastian Ziani de Ferranti, Lucien Goulard, and Galileo Ferraris. A prototype of the high-efficiency, closed-core shunt connection transformer was made by the Hungarian ZBD team at Gans Works in 1884. The new ZBD transformers were 3.4 times more efficient than the open-core bipolar devices of Goulard and Gibbs. Transformers in use today are designed based on principles discovered by the three engineers. Their patents included another major related innovation, the use of parallel connected power distribution. Otto Cubed-Blythe also invented the first AC electricity meter. The reliability of the AC technology received impetus after the Gans Works electrified a large European metropolis, Rome in 1886. In North America, one of the believers in the new technology was George Westinghouse. Westinghouse was willing to invest in the technology and hired William Stanley, Jr. to work on an AC distribution system using step-up and step-down transformers of a new design in 1886. After Stanley left Westinghouse, Oliver Schellenberger took control of the AC project. In July 1888, George Westinghouse licensed Nikola Tesla's U.S. patents for a polyphase AC induction motor and transformer designs and hired Tesla for 1 year to be a consultant at the Westinghouse Electric and Manufacturing Company's Pittsburgh labs. Westinghouse purchased a U.S. patent option on induction motors from Galileo Ferraris in an attempt to own a patent that would supersede Tesla's. But with Tesla's backers getting offers from another capitalist to license Tesla's U.S. patents, Westinghouse concluded that he had to pay the rather substantial amount of money being asked to secure the Tesla license. Westinghouse also acquired other patents for AC transformers from Lucien Goulard and John Dixon Gibbs. The war of currents involved both American and European companies whose heavy investments in one current type or the other led them to hope that use of the other type would decline, such that their share of the market for their current type would represent greater absolute revenue once the decline of the other current type enabled them to expand their existing distribution networks. Electric power transmission, the competing systems. Edison's DC distribution system consisted of generating plants feeding heavy distribution conductors, with customer loads tapped off them. the system operated at the same voltage level throughout. For example, 100-volt lamps at the customer's location would be connected to a generator supplying 110 volts, to allow for some voltage drop in the wires between the generator and load. The voltage level was chosen for convenience in lamp manufacture. High-resistance carbon filament lamps could be constructed to withstand 100 volts, and to provide lighting performance economically competitive with gas lighting. At the time it was felt that 100 volts was not likely to present a severe hazard of fatal electric shock. To save on the cost of copper conductors, a 3-wire distribution system was used. The 3 wires were at plus 110 volts, 0 volts and a 110 volts relative potential. 100-volt lamps could be operated between either the plus 110 or a 110-volt legs of the system and the 0-volt neutral conductor, which carried only the unbalanced current between the plus and a sources. The resulting 3-wire system used less copper wire for a given quantity of electric power transmitted, while still maintaining low voltages. Even with this innovation, the voltage drop due to the resistance of the system conductors was so high that generating plants had to be located within a mile or so of the load. Higher voltages could not so easily be used with the DC system because there was no efficient low-cost technology that would allow reduction of a high transmission voltage to a low utilization voltage. In the alternating current system, a transformer was used between the high-voltage distribution system and the customer loads. Lamps and small motors could still be operated at some convenient low voltage, but the transformer would allow power to be transmitted at much higher voltages, say, 10 times that of the loads. For a given quantity of power transmitted, the wire cross-sectional area would be inversely proportional to the voltage used. Alternatively, the allowable length of a circuit, given a wire size and allowable voltage drop, would increase approximately as the square of the distribution voltage. This meant that fewer, larger generating plants could serve the load in a given area. Large loads, such as industrial motors or converters for electric railway power, could be served by the same distribution network that fed lighting, by using a transformer with a suitable secondary voltage. Edison's response to the limitations of direct current was to generate power close to where it was consumed and install large conductors to handle the growing demand for electricity, but this solution proved to be costly, impractical and unmanageable. Edison and his company would have profited from the construction of the multitude of power plants required to make electricity available in many areas. Direct current could not easily be converted to higher or lower voltages. This meant that separate electrical lines had to be installed to supply power to appliances that used different voltages, for example, lighting and electric motors. This required more wires to lay and maintain, wasting money and introducing unnecessary hazards. Some deaths in the Great Blizzard of 1888 were attributed to collapsing overhead power lines in New York City. Low-frequency alternating currents can be more dangerous than similar levels of DC since the alternating fluctuations can cause the heart to lose coordination, inducing ventricular fibrillation, a deadly heart rhythm that must be corrected immediately. Any practical distribution system will use voltage levels sufficient for a dangerous amount of current to flow, whether it uses alternating or direct current. As precautions against electrocution are similar for both AC and DC, the technical and economic advantages of AC power transmission outweighed this theoretical risk, and it was eventually adopted as the standard worldwide. Transmission loss. The advantage of AC for distributing power over a distance is due to the ease of changing voltages using a transformer. Available power is the product of current voltage at the load. For a given amount of power, a low voltage requires a higher current and a higher voltage requires a lower current. Since metal conducting wires have an almost fixed electrical resistance, some power will be wasted as heat in the wires. This power loss is given by Joule's laws and is proportional to the square of the current. Thus, if the overall transmitted power is the same, and given the constraints of practical conductor sizes, high current, low voltage transmissions will suffer a much greater power loss than low current, high voltage ones. This holds whether DC or AC is used. Converting DC power from one voltage to another requires a large spinning rotary converter or motor generator set, which was difficult, expensive, inefficient, and required maintenance, whereas with AC the voltage can be changed with simple and efficient transformers that have no moving parts and require very little maintenance. This was the key to the success of the AC system. Modern transmission grids regularly use AC voltages up to 765,000 volts. Power electronic devices such as the mercury arc valve and thyristor made high-voltage direct current transmission practical by improving the reliability and efficiency of conversion between alternating and direct current, but such technology only became possible on an industrial scale starting in the 1960s. Alternating current transmission lines have losses that do not occur with direct current. Due to the skin effect, a conductor will have a higher resistance to alternating current than to direct current. The effect is measurable and of practical significance for large conductors carrying thousands of amperes. The increased resistance due to the skin effect can be offset by changing the shape of conductors from a solid core to a braid of many small wires. Total losses in systems using high-voltage transmission and transformers to reduce the voltage are very much lower than DC transmission at working voltage. Current wars. Edison's publicity campaign. Edison carried out a campaign to discourage the use of alternating current, including spreading disinformation on fatal AC accidents, publicly killing animals, and lobbying against the use of AC in state legislatures. Edison directed his technicians, primarily Arthur Kennelly and Harold P. Brown, to preside over several AC-driven killings of animals, primarily stray cats and dogs but also unwanted cattle and horses. Acting on these directives, they were to demonstrate to the press that alternating current was more dangerous than Edison's system of direct current. He also tried to popularize the term for being electrocuted as being Westinghoused. Years after DC had lost the War of the Currents, in 1903, his film crew made a movie of the electrocution with high-voltage AC, supervised by Edison employees, of Topsy, a Coney Island circus elephant which had recently killed 3 men. Edison opposed capital punishment, but his desire to disparage the system of alternating current led to the invention of the electric chair. Harold P. Brown, who was being secretly paid by Edison, built the first electric chair for the state of New York to promote the idea that alternating current was deadlier than DC. When the chair was first used, on August 6, 1890, the technicians on hand misjudged the voltage needed to kill the condemned prisoner, William Kemmler. The first jolt of electricity was not enough to kill Kemmler, and only left him badly injured. The procedure had to be repeated and a reporter on hand described it as an awful spectacle, far worse than hanging. George Westinghouse commented, "They would have done better using an axe." Willamette Falls to Niagara Falls, Indiana, 1889, the first long-distance transmission of DC electricity in the United States was switched on at Willamette Falls Station, in Oregon City, Oregon. In 1890 a flood destroyed the Willamette Falls DC power station. This unfortunate event paved the way for the first long-distance transmission of AC electricity in the world when Willamette Falls Electric Company installed experimental AC generators from Westinghouse in 1890. That same year, the Niagara Falls Power Company and its subsidiary Cataract Company formed the International Niagara Commission composed of experts, to analyze proposals to harness Niagara Falls to generate electricity. The commission was led by Sir William Thomson and included a Luther Muscat from France, William Unwin from England, Coleman Sellers from the US, and the copyright Odor Turretini from Switzerland. It was backed by entrepreneurs such as J.P. Morgan, Lord Rothschild, and John Jacob Astor. Among 19 proposals, they even briefly considered compressed air as a power transmission medium, but preferred electricity. But they could not decide which method would be best overall. International Electrotechnical Exhibition. The International Electrotechnical Exhibition of 1891 featured the long-distance transmission of high-power, three-phase electric current. It was held between May 16 and October 19 on the disused site of the three former OE Westbahnhof Paragraph A in Frankfurt am Main. The exhibition featured the first long-distance transmission of high-power, three-phase electric current, which was generated 175 km away at Laufen am Neckar. It successfully operated motors and lights at the fair. When the exhibition closed, the power station at Laufen continued in operation, providing electricity for the administrative capital, Heilbronn, making it the first place to be equipped with three-phase AC power. Many corporate technical representatives attended. The technical advisors and representatives were impressed. AC deployment at Niagara. In 1893, NFPC was finally convinced by George Forbes to award the contract to Westinghouse, and to reject General Electric and Edison's proposal. Work began in 1893 on the Niagara Falls generation project. Power was to be generated and transmitted as alternating current, at a frequency of 25 Hz to minimize impedance losses in transmission. Some doubted that the system would generate enough electricity to power industry in Buffalo. Tesla was sure it would work, saying that Niagara Falls could power the entire eastern United States. None of the previous polyphase alternating current transmission demonstration projects were on the scale of power available from Niagara. The Laufen-Neckar demonstration in 1891 had the capacity of 225 kW. Westinghouse successfully used AC in the commercial Ames hydroelectric generating plant in 1891 at 75 kW. The Chicago World's Fair in 1893 exhibited a complete 11,000 kW polyphase generation and distribution system with multiple generators, installed by Westinghouse. Armeri and Decker designed a three-phase 250 kW AC system at Mill Creek, California. In 1893, on November 16, 1896, electrical power was transmitted to industries in Buffalo from the hydroelectric generators at the Edward Dean Adams Station at Niagara Falls. The generators were built by Westinghouse Electric Corporation using Tesla's AC system patent. The name plates on the generators bore Tesla's name. To appease the interests of General Electric, they were awarded the contract to construct the transmission lines to Buffalo using the Tesla patents. Competition outcome. As a result of the successful field trial in the International Electrotechnical Exhibition of 1891, three-phase current, as far as Germany was concerned, became the most economical means of transmitting electrical energy. In 1892, General Electric formed and immediately invested heavily in AC power. Westinghouse was already ahead in AC, but it only took a few years for General Electric to catch up, mainly thanks to Charles Protestantmitz, a Prussian mathematician who was the first person to fully understand AC power from a solid mathematical standpoint. General Electric hired many talented new engineers to improve its design of transformers, generators, motors and other apparatus. In Europe, Siemens and Halske became the dominant force. Three-phase 60 Hz at 120 volts became the dominant system in North America, while 220 to 240 volts at 50 Hz became the standard in Europe. Alternating current power transmission networks today provide redundant paths and lines for power routing from any power plant to any load center, based on the economics of the transmission path, the cost of power, and the importance of keeping a particular load center powered at all times. Generators can be located far from the loads. Remnant and existent DC systems. Some cities continued to use DC well into the 20th century. For example, central Helsinki had a DC network until the late 1940s, and Stockholm lost its dwindling DC network as late as the 1970s. A mercury arc valve rectifier station could convert AC to DC where networks were still used. Parts of Boston, Massachusetts along Beacon Street and Commonwealth Avenue still used 110 volts DC in the 1960s, causing the destruction of many small appliances used by Boston University students, who ignored warnings about the electricity supply. New York City's electric utility company, Consolidated Edison, continued to supply direct current to customers who had adopted it early in the 20th century, mainly for elevators. The New Yorker Hotel, constructed in 1929, had a large direct current power plant and did not convert fully to alternating current service until well into the 1960s. This was the building in which AC pioneer Nikola Tesla spent his last years, and where he died in 1943. In January 1998, Consolidated Edison started to eliminate DC service. At that time there were 4,600 DC customers. By 2006, there were only 60 customers using DC service, and on November 14, 2007, the last direct current distribution by Con Edison was shut down. Customers still using DC were provided with on-site AC to DC rectifiers. The Central Electricity Generating Board in the UK continued to maintain a 200-volt DC generating station at Bankside Power Station on the River Thames in London as late as 1981. It exclusively powered DC printing machinery in Fleet Street, then the heart of the UK's newspaper industry. It was decommissioned later in 1981 when the newspaper industry moved into the developing Docklands area further down the river. The building was converted into an art gallery, the Tate Modern. Electric railways that use a third rail system exclusively employ DC power between 110 and 1500 volts. Railways with overhead catenary lines use various power schemes including both high-voltage AC and low-voltage DC. Low voltage in this context is 5 kV or below. High-voltage direct current systems are used for bulk transmission of energy from distant generating stations or for interconnection of separate alternating current systems. These HVDC systems use electronic devices like mercury arc valves, thyristors or IGBTs that were unavailable during the War of Currents era. Power is still converted to and from alternating current at each side of the modern HVDC link. The advantages of HVDC over AC systems for bulk transmission include higher power ratings for a given line and better control of power flows, especially in transient and emergency conditions that can often lead to blackouts. Many modern plants now use HVDC as an alternative to AC systems for long-distance, high-load transmission, especially in developing countries such as Russia, China, India and Brazil. One of the principal advantages is the ability to transfer power between two AC systems that are not synchronized in phase. DC power is still common when distances are small, and especially when energy storage or conversion uses batteries or fuel cells. These applications include electronics, including integrated circuits, high-power transmitters and computers, vehicle starting, lighting, and ignition systems, hybrid and all-electric vehicle propulsion with internal power supply, telecommunication plant power, uninterruptible power for computer systems, utility-scale battery systems, off-grid isolated power installations using wind or solar power. In these applications, direct current may be used directly or converted to alternating current using power electronic devices. In the future, this may provide a way to supply energy to a grid from distributed sources. For example, hybrid vehicle owners may rent the capacity of their vehicle's batteries for load leveling purposes by the local electrical utility company. See also. References. Further reading, Burton, Pierre. Niagara, A History of the Falls. New York, Kodansha International. Bourdieu, Sanford P. Volts to Hertz Euro The Rise of Electricity, From the Compass to the Radio through the works of 16 great men of science whose names are used in measuring electricity and magnetism. Minneapolis, Minnesota, Burgess Pub Company. Brandon, Craig. The Electric Chair, An Unnatural American History. Jefferson, North Carolina, McFarland and Company. Edquist, Charles, Homan, Leif, and Sapuri, Lena J. Public Technology Procurement and Innovation. Economics of Science, Technology, and Innovation, v. 16. Boston, Kluwer Academic. The Electrical Engineer, A New System of Alternating Current Motors and Transformers, London, Biggs and Company. Pages 568 to 572. The Electrical Engineer, Practical Electrical Problems at Chicago, London, Biggs and Company. Pages 458 to 459, 484 to 485, and 489 to 490. Foster, Abram John. The Coming of the Electrical Age to the United States. New York, Arno Press. Hughes, Thomas Park. Networks of Power, Electrification in Western Society, 1880 to 1930. Baltimore, Johns Hopkins University Press. Tom McNichol ACDC, The Savage Tale of the First Standards War, John Wiley & Sons, 2006 ISBN 0-7879-8267-9, Reynolds, Terry S., and Bernstein, Theodore. A OE Edison and the Chair, a IEEE Technology and Society Magazine, March 1989, ppA 19 a 28. Seifer, Mark J. Wizard, The Life and Times of Nikola Tesla Biography of a Genius. Secaucus, New Jersey Carroll Pub. External links, Thomas Edison Hates Cats, AC vs. DC, an online video mini-history. War of the Currents. PBS. War of the Currents nuke.berkeley.edu